Thanks for tuning into this Revision Zone Maths video. In this video, we'll be looking at some standard results with regards to differentiation. So result one is quite interesting. It says that if we've got a function y equals f of x, that's just a regular function, then of course we can differentiate it directly, but the result tells us one way of differentiating y with respect to x is actually to put 1 over dx by dy. So in other words, you go to y equals f of x and you go from that function to writing down the inverse function, f inverse of y is equal to x, and you differentiate that function, and then you put 1 over that function, and the answer, the result says, is the exact same as just differentiating our initial function directly. Of course, one important thing to keep in mind is the inverse function differentiated better not be 0. So the stationary points of the inverse function are actually going to give us problems here, right? We can see why that is. So proof, we're going to use the chain rule. And of course, we know that the chain rule says if I've got dy by du and then I multiply by du by dx, the result is the same thing as having dy by dx because of this chain with u, making sure that we can go from y to x directly, which is what the right hand side says. So now we're going to have a quite quirky application of the chain rule. So how about we think about something like dy by dx, but then we make the chain with x, so we write down dx by dy. And of course, following the exact same format of the chain rule here, we can write down dy by dy, okay? So this is completely algebraically and structurally fine because it's just a restatement of the chain rule with just the variables now jumbled up in a rather interesting way. So at this stage, the only thing we've got to do is give meaning to dy by dy, right? So we can sort of do that on the side here. So we can say take y equals y, and now this is true for every single y that you can think of, and then I can just differentiate the left-hand side with respect to y, and well, what's the right-hand side going to give me? Y differentiated with respect to y is just 1. So in other words, we know that that is dy by dy, so y differentiated with respect to y is 1. So I come back to the statement here, and I basically say let me write it here. Dy by dx times by dx by dy is actually equal to 1, which we can simply rearrange to say dy by dx is actually equal to 1 over dx by dy, where, of course, dx by dy does not equal 0, y equals f of x, uh, and by extension x equals f inverse of y. So indeed, in working out this dx by dy, we get this function and then we differentiate it just as I said earlier. So that's the proof completed. Perhaps it's worth looking at another way of being able to write this if you weren't able to follow what I've just done here. So let's start again. So we define the function capital F, and it's defined as f of g of x. And of course, we want our g of x to be the inverse function f. I could have written the inverse function there already, but I felt that would have made things a bit more messier. So I've sort of written it in a slightly different way. But of course, what we want to do is we want to have lowercase f as just a function of everything on the inside, and we take that to be u, so y is actually a function of u, right? But now let's think about this capital F. Since capital F is f of g of x, but g is the inverse of f, then capital F is f of f inverse of x, which means capital F is just actually x, right? Which is what we have here. So since capital F is just x, that tells us from the definition of y that y is actually just x, which means we can differentiate the statement directly to say dy by dx is just 1 because x differentiates to give us 1. And then we can put that back into the chain rule statement. So just sort of reorganizing the way the chain rule is written, I can actually have this statement here where my dy by dx has actually now been put to 1. So at this stage, we see we're nearly there. We just want to be able to massage this to be in the right sort of form, and then we can sort of make our conclusion. So what can we actually say exactly here? Well, since y is actually equal to x, then I know when I differentiate u with respect to x, that's exactly the same as differentiating u with respect to y, because x and y are actually exactly the same. And it's important to see here, I've actually put 3 equal signs. So I'm saying it's not just that they're equal for some special values. No, 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 no. They're actually equivalent. They're mathematically identical, right? So since I have this identity because of the fact that y and x are identical, then I can come back to my statement here and I can say this du by dx, I can just use this identity to replace it by du by dy. And here you go, we're basically done. So at that stage, we just rearrange that to say then dy by du has to be 1 over du by dy, okay? And of course, du by dy can't actually be 0. Now, you might look at this and say, hang on, the last statement that we proved was dy by dx is equal to 1 over dx by dy. So at this stage, I would say to you, look at our function. Y is actually lowercase f of u. It's not lowercase f of x, which was the case in our working in the previous result. So since y equals f of u was defined to be the case here, then our result one precisely takes the form of the statement in the yellow box. Okay? So we've managed to arrive at the exact same result by basically the same sort of argument, just laid out in a slightly different way. So let's take a look at result 2. Result 2 is basically going to allow us to be able to differentiate natural log functions, and we can jump straight in with actually a solution. So I can say let y equals log x. Okay, then I'm actually going to use the statement we worked out before, that dy by dx is equal to 1 over dx by dy, where of course dx by dy better not be 0, because otherwise this thing's not sensible. So since we actually know y equals log x, then I can take exponentials of both sides and I can say e to the y is actually equal to x. And since I have this, I can actually say x equals e to the y tells me that dx by dy, because we can differentiate exponentials and they give us the exact same thing, actually is e to the y. But now I can go to this result and say that then tells me that my dy by dx is actually equal to 1 over e to the y. Okay, so we've basically worked out the derivative. The problem is we want to write down our derivative explicitly as a function of x. So what we're going to do is we're going to come here and say, well, we know what e to the y is. It's just x. So that e to the y can just be replaced directly by x. And I can actually say that dy by dx is actually 1 over x. And of course, x better not be 0. Let's think about extending this result. So in fact, what we can say, if y is log of actually any function f of x where f of x is differentiable, then dy by dx is actually f prime x over f of x, where of course where f of x better not be 0, where f of x is not 0. In other words, we can't consider values of x for which f of x actually becomes 0. So let's see why this might be true. Just quickly as an aside, well, what we're going to do is we're going to apply the chain rule. So I'm going to say let u equals f of x, then I'm going to say dy by dx is equal to the dy by du times by du by dx. But since u equals f of x, then du by dx is just f prime x, and that's fine. But since u equals f of x, then what I can actually say y equals log of f of x is actually just log of u, which tells me that actually dy by du by the result we've worked out on the left is just 1 over u. So I can now go put both these things into my chain rule formula, and I can say that dy by dx is actually 1 over u times by f prime x. But what is u? Well, it's just u is just f of x, right? So when I multiply this out, the 1 times f prime just gives me f prime on the top, and the u at the bottom just becomes f of x. And of course, I've just got to say f of x cannot actually be 0. So all the values of x for which f of x is 0 are actually excluded. And we've been able to arrive at an extension of our result. So result 3 is another very interesting result, and in this case we can actually show that if you have the function y equals a to the x, for indeed a being any sort of positive number, then you can work out the derivative, and the derivative is log a times by a to the power x. Okay, so let's see why this result is true. Again, we're going to go back and use result 1 again here, but let me say let y equals a to the x, where a is positive. Of course, we're going to use dy by dx is equal to 1 over dx by dy. So to be able to use this result, I'm going to have to invert my a to the x function. How am I going to invert it? I'm just going to take logs of both sides, log of a to the x, and of course, using one of the properties of logs, we can actually say you can bring the power down, and at this stage, I can actually rearrange this to say x equals log y over log a. And I now have a function in a suitable form that I can differentiate. So differentiating above with respect to y gives me that dx by dy. Now I've got to be careful here because that is just a number, right? So the log a is just a number. So I'm just going to have, because a is a constant, so I'm going to have the log a by itself on the outside. And then the log function, well, we saw how to differentiate that in the previous result, right? So I know it's just going to be 1 over y in this case, which I can simplify to say it's going to be 1 over log a times by y, but I know what y is. Y is a to the x, so it's going to be log a times by a to the x. I'm deliberately writing it in this form because I want my final answer written in that form. So once we have this, we can go back to our key statement that I've marked as a star, and then we can say sub into star, and what do we get? We get dy by dx is actually equals to 1 over log a times by a to the x, and when you do the algebra, it's just going to be log a times by a to the x, and we're done. Just as before, let's think about an extension of the rule of the result we've just worked out. So in this case, I will say let u equals f of x, and we see our statement goes from being y equals a to the f of x to being a to the u. And now I can basically use the chain rule to say dy by dx is equal to dy by du times by du by dx, and we know that from u equals f of x that our du by dx is just f prime of x, and we also know from in fact the work on the left hand side that dy by du, because our y is a to the u, is just going to be log a times by a to the u. So indeed what we end up with here is going to be log a times by a to the u times by f prime x. And substituting u equals f of x into this and just sort of changing the order of the multiplication, which is perfectly allowed, I can actually say this, which is precisely what we actually wanted to show. It is worth making some more remarks here. I'll just make some room to be able to make those remarks. So let us try and see what happens to result 3 when we actually take a to be e, right? So we say take a to actually be e, then what we actually have is y equals a to the x is actually y equals e to the x, and of course e is bigger than 0, so that's completely fine. And the result above tells us that when I actually take the derivative, what I should get is I should get log of a, which is obviously e, times by e to the power x, okay? But log of e is of course just 1, so it's just 1 times by e to the power x, which is just e to the power x. So this is very reassuring because this is exactly consistent with what we worked out as a derivative of e to the x before. So that's the first thing. And the second thing to keep in mind is actually we can use the extension of the result to say something about what happens when we're differentiating complicated versions of e to the x. So again, so we say take a to actually be e, then that tells us that y equals a to the x is actually just e to the x. But in this case, we don't want e to the x. We actually want a to the f of x, and we also want e to the f of x. This is better. And of course, e is positive. Then using the above result, what we can say that the derivative in this case is actually just going to be, we're going to have our log a. So we're going to have our log e. So log of e. Then we're going to have f prime. So our f prime is just going to be the derivative of f, which is going to be f prime x. And then lastly, we're going to have a to the power f of x, but our a is e. So we're going to have e to the power f of x. And just like before, log e is just 1, right? So we can just say, so finally we end up with, to differentiate e to the power f of x, we just write down e to the power f of x and multiply that by f prime x. It's a very easy formula for differentiating potentially very, very difficult looking functions. So for the remainder of this video, we're just going to work out some standard results that are actually on the formula sheet. And in particular, these are sort of some standard trig functions. So let's start with a tan, because we've already seen how to differentiate sines and cosines. So we're going to start with y equals tan x. And of course, the easy way of doing this is to writing this as a sine over a cos. And the moment I say that, I better say we're only considering cases where cos is non-zero. And then at this stage, we're going to use the quotient rule. So I'm going to say let u equals sine x and v equals cos x. We've seen this sort of thing sort of lots of times before, so I'm just going to start to simply work my way through this systematically. The derivative of sine is cos, and the derivative of cos is minus sine. And of course, the quotient rule actually says, and then we just substitute things in. So I come here and do the substitution. My v is cos x. My du dx is also cos x, right? I can see that from sort of here and here. So that's my v, and that's my du dx. And then I have a minus sign, and then my u is sine x, and my dv dx is minus sine x. And then the whole thing is actually over v squared, which is obviously cos squared. Cos x, and let's put a squared there. Then just simplifying this, the first term becomes cos squared x, and the two minuses actually give me a plus, so I get plus sine squared x, and the whole thing is then over obviously cos squared x, right? And at this stage, because we know cos squared plus sine squared is 1, it's just 1 over cos squared x, and of course that's just sec squared x. That's the definition of sec. Okay, so it's just sec squared x, and we're done. And of course, as before, we can actually work out an extension to this sort of a derivative, which is if you actually have the tan of any differentiable function f of x, then when you differentiate it, you just get sec squared of f of x, but you've got to multiply by f prime. Okay, so let's see again why this may be true, which is so if we take u equals f of x, that tells us that y equals tan of u. But then looking at this, I know that my du by dx is equal to f prime x, and we also know that our dy by du is just, because we know y is tan u, then dy by du using the result we've just worked out, shown in this result, in fact, is just sec squared u. So sec squared u. But then putting all this together, what we can say is we know that dy by dx is dy by du times by du by dx. Well, okay, our du by dx is here. That's f prime. So I'm just gonna write that. And of course, dy by du is just sec squared u. But what is u? U is just f of x. This is indeed the exact result that we actually wanted to show, so let's move on to the next result. So result 5, the function we're looking at is sec x, and its derivative works out to be sec x tan x. So we can just jump straight in and actually calculate this. So y equals sec x, but of course it's easier to deal with it as 1 over cos x. And when I say this, I've got to say that cos x better not be 0. So how are we going to differentiate this? Well, we can differentiate it using the quotient rule, but I think it's easier to differentiate it by basically saying it's cos x to the minus 1. And now we can use a version of the chain rule. So we've already shown before that if we've actually got something of the form, perhaps I should write it in a different color. If we've got something of the form y equals f of x to the n, then actually dy by dx is actually just n f of x to the n minus 1 times by f prime x, where n is obviously any real number. So we're gonna use this result in red, and going back to our function in black. So we've got the function is cos x and n is minus 1. So when I actually differentiate the function, I get dy by dx. So first of all, I've got to write down my n. My n is minus 1. Then I've got to multiply by the function, which is cos x to the power 1 less than what I started with. So I started with minus 1, so I'm going to end up with minus 2. And then I have to finally multiply by the derivative of my function, right? So my function is cos, the derivative of cos is minus sine. So you see, we've been able to write down the answer, and in this case, it's just going to be sine x over cos squared x, but obviously we can split that up into a sine x over cos x times by 1 over cos x, and that's the exact same thing as tan x times by sec x. So let's quickly take a look at the extension result in this case. So again, we've actually replaced x in the first instance by the function f of x. And what we find is we don't just get the same thing as we got the first time, we actually get the same thing, but we have it multiplied by f prime. Okay? So we say take u equals f of x. That then tells us that y is actually sec of u. And let's do the same sort of thing we did last time. Well, we know what du by dx is. We can work that out from here. So if u is f of x, then du by dx is just f prime of x. And we also know what dy by du is, because if y equals sec u, then dy by du, using the result we've already worked out above, is just going to be sec u tan u. Okay, this is the result that we've actually got above. So now we can just use the chain rule to say dy by dx equals dy by du times by du by dx. And for reasons of space, I'll not put this in, but you can sort of do this yourself and just check that actually you get the exact same thing as we've sort of claimed here. So result 6, we're continuing our exploration of differentiating trig functions, if obviously. So in this case, we've got the cosec function, and we want to show its derivative is minus cosec cot. So let's again just do this fairly directly. There are lots of ways of doing this, but I'm going to just use the chain rule because I find that that's just the most sort of direct. So I say y equals cosec x, which we want to write down as 1 over sine x, which is of course the definition of cosec. And when I say that, I've got to say that we better have sine x not being equal to 0. But then we want to write this as sine x and the whole thing to the power minus 1. So again, we want to use the formula that I wrote down last time. So if we've got a function of the form f of x to the power n, then we've seen before that its derivative actually is n f of x to the n minus 1 times by f prime of x, where n is actually some real number. Okay, so I'm going to do this slightly more briefly in this case. So since our function, so take f of x equals sine x and n equals minus 1, then we basically have our derivative as being minus 1 times by sine x to the minus 2 times by the derivative of sine is obviously cos, so cos x, which we can simplify to say it's minus cos x over sine squared x, which of course is minus cos x over sine x times by 1 over 1 over sine x, which is minus cot x cosec x. Let's again quickly just look at the extension. The extension of this is going to be, well, if you had y equals cosec of f of x, then what you actually have is when you differentiate it, you should get minus cosec f of x cot f of x, and then you should have an f prime at the front, okay? And I didn't put the minus from earlier. So that's what you'll get. I won't run through the entire details. You may actually check this. So I'll say take u equals f of x, then y equals cosec u, and apply the chain rule. Okay, so perhaps we can move on to the next result. So since we've seen the derivatives for tan, sec, and cosec, it's not surprising that the only one that's left is actually cot. And after we've done this, we will have seen derivatives of all the standard functions, all the standard trig functions at least. So we will have done sine, cos, tan, sec, cosec, and finally cot. So let's differentiate this. So I'm going to just write down the function cot, but we want to write cot down as a fraction, as a quotient, so cos over sine. And the minute I say this, I better say sine x is not 0. Of course, I should also emphasize when I write down cot, there are values of x for which cot is not defined. So technically, I should write down those values of x, or at least some description of them. But obviously, I've got around that by just basically writing them down in the form that sine cannot be 0 at those points. They're going to be the same values for x. So anyway, so at this stage, I think you would agree that it's hopefully easy to just use the quotient rule. So we say take y equals, so maybe I could write it here, take y equals u over v, where u is actually cos and v is actually sine. Then to use the quotient rule, we're going to have to differentiate cos. The derivative of cos is minus sine. And we're going to have to also differentiate sine, and the derivative of sine is, of course, cos. So we can write down the quotient rule formula. So the quotient rule formula, so I'm now just going to come and start to substitute things in directly. And we've already seen a lot of this that I've done before. So we know our v is basically sine, so I'm going to write down sine. And our du by dx is minus sine, so I'm going to write down times by minus sine. Then we have the minus sign. And then we have u. So our u is just cos, so I'm going to write down cos. And then finally for the numerator we have dv by dx, which is actually just also cos, so I'm going to write that down. And our denominator is going to be, of course, just v squared, but v is sine, so it's just going to be sine x squared. And just simplifying things in the numerator, I get minus sine squared x minus cos squared x, and then this is all over sine squared x, and I can take out a minus here. So we end up with that, but of course the numerator is just going to be 1 because sine squared plus cos squared is actually equal to 1. So I'm going to write that down. And then the denominator is going to remain sine squared, which of course another way of writing that is just cosec squared. And the negative one at the front just comes along to the right. So we've actually differentiated our function. So just again, a very quick word on the extension. This shouldn't surprise you given what we've seen so far. If I go back and replace my x with the function f of x, then the answer is going to be the same. The derivative is going to be the same. It's going to be cosec squared of, I should have corrected this. This should actually be f of x. So we're going to have cosec squared of f of x, but then the only catch is we've got to remember to put a derivative of f out at the front as a product, right? So how we're going to show this? Well, again, I won't go through all the details. I'll just say take u equals f of x, so that y equals cot of u, and then apply the chain rule. Then apply the chain rule. Result 8 is something that's actually quite easy, and it's really just the extension of differentiating standard sines and cosines. That's why I've put both the statements together as sort of one result. And perhaps it's quickly just worth sort of going through this just so we're all clear how this works. So let's look at the first result. I want to differentiate sine of f of x. We're just going to use the chain rule. So I'm going to say let y equals sine of f of x and u equals f of x. So the minute we have that then tells me that y is actually equal to sine of u. But now I can start to differentiate these because I know my du by dx is just going to be f prime of x. And I also know that my dy by du, because sine differentiates to give me cos, will just actually be cos u. So now by chain rule, so chain rule, we have that dy by dx is actually equal to dy by du times by du by dx. Dy by du is just cos u, and du by dx is just f prime. We've just worked them out above. And now we can just sort of change the order because multiplication is commutative and replace the u with what we've defined u to be, which is f of x. So f of x. And we've basically figured out the very first statement that we actually wanted to show. So we give ourselves a tick, and we can repeat this for the second statement. And I hope you would forgive me for just being a bit quick this time. So u equals f of x again. So that tells us y equals cos u, and du by dx is actually f prime x, and dy by du, differential of sine, cos is minus sine, so I write that down. Then by the chain rule, we can just say it's dy by du times by du by dx, which is minus. So tidying all this up, we end up with minus f prime x times by sine of x, which of course is exactly the same thing that we actually wanted to show. So we have that here. So we give ourselves a tick and we move on to the next example or the next result. So result 9 is rather interesting. We've actually got the inverse sine function. I've just written it as arcsin just to make sure it doesn't get confused with the reciprocal of sine. And we want to show that when you actually differentiate it between minus 1 and 1, you actually get 1 over 1 minus x squared square rooted. So let's work that out. So in fact, we start with our function arcsin x, and I should say x has to be between minus 1 and 1. And then if I take the sine of this on both sides, then since the arcsin and the sine are inverse functions, they actually cancel, and I just end up with x. Okay? So at this stage, I can differentiate. So I know that x equals sine y, for example. So knowing x as a function of y, I can just differentiate to say dx by dy actually equals cos y, right? And now we turn to result 1, in which we showed that dy by dx is actually 1 over dx by dy. And since dx by dy is cos y, I should say cos y, and the minute we say that, we better say cos y does not actually equal to 0, but we can sort of work around that. So we want to express our derivative in terms of x, not in terms of y. So we say, let's use the identity cos squared y plus sine squared y is equal to 1, and that really tells me that cos squared y is equal to 1 minus sine squared y, which then goes on to tell me that actually cos y is the square root of 1 minus sine squared y, and then I can now substitute this in. So of course, upon doing that, we just end up with 1 over cos y being 1 over the square root of 1 minus sine squared y. So we know from the work we did earlier that sine y is actually just x. So we now come here and say that's the same thing as 1 over the square root of 1 minus x squared, and the whole thing is square rooted. And perhaps we will say that x has to be between minus 1 and 1, because this is a function that's probably unfamiliar to most on the A-level syllabus. And the reason why x has to be between -1 and 1 is obviously you can't take the inverse of things like 5 or 7, because if you think about the nature of the sine graph basically only does something like that, which means the maximum value here is 1 and the minimum value is -1. So it doesn't really, it's not possible to have an output of 5 or 16 for a standard sine function. So it makes no sense to say, well, what's the inverse of 5 or 16? But the other important point here is why it can't be equal to 1 for the inverse function is because if it actually equals 1 or -1, then this x squared becomes 1 and you get 1 minus 1 going to 0, which then gives you a problem with 1 over 0. So a remark worth mentioning here might be that actually you can go and repeat all of this for not the inverse sine function, but for the inverse cos function. And again, that's only valid for x being between -1 and 1. And you can show the derivative actually works out to be negative of 1 over 1 minus x squared square rooted. Okay, so our last result is also another inverse function, but in this case we have the inverse tan function. And we want to show that when we differentiate the inverse tan function, we actually get 1 over 1 plus x squared. Now, the interesting thing here is that this is actually well defined for every single real number, and so is the derivative well defined for every single real number. And of course, the reason for that is as a function, the tan function actually gives out every single output on the y-axis. So when you want to take the inverse, you can actually go to anything on the y-axis and get an inverse on the x-axis. Okay, so I'll just make a bit of room and then get started with this result. So let's dive into the calculation. We're going to start with y equals arctan of x, and we want to invert it because we want to be using the result that dy by dx is actually 1 over dx by dy, because otherwise it's going to be too hard to differentiate directly. So inverting the function, I just apply tan to both sides. So I take tan to the other side, and of course the tan and the arctan are going to cancel to just give me tan y equals x, right? But once I know that x equals tan y, then I can differentiate this function x of y with respect to y, and I know what the derivative of tan is because we worked this out in this video. It's just sec squared. So I actually end up with sec squared y, and I can go back and substitute into the formula for dy by dx. I get 1 over sec squared y, because obviously our dx by dy is exactly that. Now, we're not quite happy leaving this in this form because we want to express the derivative as a function of x. So what we're going to say is cos squared y plus sine squared y equals 1, and we divide this statement by cos squared y to be able to get 1 plus tan squared y equals sec squared y. So now we can go back and say 1 over sec squared is just 1 plus tan squared y, but luckily we know what tan y is, it's just x. So 1 over 1 plus tan squared y is just 1 over 1 plus x squared, and we've been able to work out our derivative. At this stage, I'd like to bring this video to an end. Thank you for watching. If there are any topics on which you would like to see more videos, do say so in the comment section. Do hit the like and subscribe buttons, and as always, we'll see you in the next video.